Welcome again to Physical Science 101. We're going to look at Chapter 4 today on the subject of work and energy. So we'll begin by sharing, let's try that again, sharing the PowerPoints. Here we go. Work and energy, Chapter 4. We should first start off with the definitions, because we haven't defined what work actually is. In the scientific sense, work is a force applied through a distance. So if you apply a force to say, move an object, and it moves a certain distance, then you have performed work that is actually the product of the force applied times the distance moved. And those units of measure, of course, will be force is newtons, and distance is in meters. So Newton meters is work. And in fact, we give it a new unit of measure. A Newton meter is equal to a joule. All right. And of course, the distance moved has to be in the same direction as the vector force. So, how much work is done if I say push against a wall? I apply force, right? The force is there. Is there any movement? More than likely, there's not. After all, I'm not King Kong. I can't move a wall with the force of my paw. So in that case, the force is applied, but no movement. There was no work done. Now in this case, a force was applied and the box was moved a distance d. So there was work performed, force times distance. Now, in this illustration, we have a force applied by the woman mowing her grass, and the force is applied down the handle of the lawnmower to the mower. But all of that force applied is not parallel to the movement of the mower. So we have to know how much of that force was actually applied parallel, which would be a vector quantity, a vector component of the force applied. So some of the force was applied vertically, some of it was applied horizontally, and the horizontal component is the force that enters the calculation for work. Okay, so here we have a discussion of the units of measure. A Newton times a meter equals a Newton meter, and a Newton meter now is called a joule. So work is given the new unit, joule, and it's named after a French polymath who did work on work, and is given credit by naming a unit of measure after him. Now, just for comparison, in the British system, a force is a pound, and the standard of measure is a foot. So a foot-pound is the British unit of measure for work. We can relate some of this back to Newton's laws of motion. When work is done and the force is applied, you will actually feel a resisting force, right? We get an action and a reaction. And very often we have to take into consideration other interacting forces, because this measurement of work is the net force times the distance moved. So you have to subtract all of the opposing forces so that you know how much net force is applied to do the work. The rest of it is, so to speak, wasted energy. Now, when we talk about gravity, very often what we're doing is we're resisting the force of gravity that's pulling us to the earth to lift an object. So in that case, we know how much force is required to lift an object because we know we can calculate the force needed to move a mass against gravity. Its weight then is equal to its mass times the acceleration of gravity. We know that because of Newton's second law. So in this case, the weight is equal to the mass times the acceleration of gravity. Okay? And if we know that this weight is the force required to lift something, then all we have to do is we know how high it is lifted from one point to the next, and that tells us how much work was required to lift the object through that distance, that height. Okay, so in that case, work then is whatever this W is, which is a product of mass times acceleration of gravity, and then times the distance. So the work done to lift something in the Earth's gravitational field is the mass times acceleration of gravity times the height, or the change in height. Now that we know what work is, we know intuitively that in order to do work, energy must be expended. And energy, by definition, is the ability to do work. It doesn't mean that work is actually done. We've already shown that. But the energy is there and available to do work. And any type of energy that a system possesses is there and available to do that work. It doesn't always, of course, happen. Now, we have to square away. If we're going to do calculations involving work and energy, we need to clarify. We have to clarify movements of work and energy. In other words, this is in terms of the system. Remember last chapter, I gave you a little diagram where we had open system, closed system, isolated system. We're going to go back to that, and this references what sign do we apply to the magnitude of the energy or the work or any other exchange that takes place with a system, so that we know what direction things are moving. Remember, all of these are vector quantities, so we have to know direction, and we specify that direction by the sign in front of the number. So when we have system and surroundings, there's our system, here's our surroundings, and we may choose that the surroundings are only that much. Everything is in reference, the sign on any magnitude or any number, the sign is always in reference to the system. If something is transferred into the system, it's a positive value. The system has gained, so it's a positive value. If anything leaves the system, it's a negative value. All right. Okay. So when work is done on the system, say something in the surroundings, say I am part of the surroundings, and the system is the lawnmower, then when I push on the system, I am doing work on the lawnmower. So the value then would be positive. And whatever the work value has to be would be a positive value. If something is pushing against me, if I'm still in the surroundings and something is pushing against me, say the system is, well, I don't know, a hurricane force wind. And the wind is the system. And it pushes on me and moves me back. Then the wind is giving up some of its energy in the form of work. And now the system has lost by doing work on me. Okay, this is one of the ways of transferring energy is to do work. So we transfer energy to this system by doing work on it, by moving it. Or it does work on the surroundings by moving the surroundings and expends energy in the process. Now this can happen in various forms. Very often it happens in the form of heat. So heat transfer. And we have a symbol that we use for heat, which is a little Q. Right? And heat is measured by a change in temperature. So in other words, if the surroundings gets colder and the system gets warmer at its expense, then heat is being transferred into the system and the value for the heat is positive because everything is referenced to the system. Now, work and energy have the same units of measure. Energy is the ability to do work, so it has the same units of measure as work, joules. Okay, so here's an illustration of surroundings and system, and we're going to transfer heat, right? Or in this case, energy, whichever the case may be. The transference here is out of the system, so the change in energy, which this is delta E, represents the change in energy, is less than 0, which means it's negative. And in this case, energy is transferred into the system, and we have a delta E that's greater than 0, and that's a positive value. Now, if this energy transfers in the form of heat, we say that it's endothermic, which means that the heat is transferred out of the system and the system gets colder. The Q in that case is positive. Oh, excuse me. Back up. I correct myself. Endothermic means into. Heat is transferred into, endothermic. So it would be this side over here where Q is positive. That is endothermic. Heat is transferred into the system. If it's transferred out of the system, that's exothermic. Okay, and those words reference heat. You know, if you see the word endothermic, that's heat is transferred into the system, into heat, and out of heat. There's another word for energy, but we won't labor you with that one. You only need to know the one referencing heat. Exothermic processes where heat leaves the system are always negative. So if you bring your hand close to a boiling pot of water, you feel the heat, which is leaving the system. That is an exothermic process. And the Q value for that system, which is the boiling pan of water, is negative. Now, when we talk about purely energy or the ability to do work, we can subdivide it into two forms. When we say there is kinetic energy in the system is moving. Something is moving in the system. Either the whole system is moving or something inside the system is moving. We call that kinetic energy. Kinetic always means motion. It's energy of motion. And we can calculate the energy of motion of any object that is moving. All we need to know is what is its mass and how fast is it moving? What's its velocity? So the kinetic energy is calculated by this expression. Mass times the square of the velocity, half of that value, is the kinetic energy of that object. Okay, they use E sub k here to be sure you understand its energy. Ke for me means the same thing. All right, if an object is already moving, then we can calculate how much energy is required to change its motion. Make it go faster, make it go slower. A change in kinetic energy requires work. Energy must be expended in the form of work to change the kinetic energy of any object. So here we're saying that the work required is a change in kinetic energy, which just means that you know the kinetic energy at the end, the final kinetic energy, and then you subtract the kinetic energy that it had before the change, and that's equal to a calculation for this is the final velocity, and that's the initial velocity, right? So this is before, this is after. These expressions are equal to each other. And of course, the units of measure will be joules. So if we take this expression and we say mass is kilograms and velocity is meters per second, but we square it. So now the units of measure are kilogram meters squared per second squared, and that's equal to energy, joules. So joules is also equal to kilogram meters squared per second squared. But we said earlier that joules is equal to Newton meters, correct? Right? So if this is equal to joules and that's equal to joules, then these two are also equal. So if we factor out a meter from this one, what do we have left over? We have kilogram meters per second squared. Okay, so this is the Newton part, and this is the distance part, the meters. But where does newtons come from? It's a force, right? So force equals mass times acceleration. Mass is kilograms. Acceleration is meters per second squared. So there's your meters per second squared. There's your kilograms. So now we have all of these things are related by the units of their measure. And that's important if you enter into a calculation and you need to combine units in that calculation. You know what each one is equivalent to, and if you need to cancel units, then you have access to these equivalences. All right. Sometimes you don't have to do that, right? If the units cancel because there's joules here and joules there, then there's no need to go this route. But if you have joules here and you have kilogram meters per second squared or some other units over here on this side, then you know what the equivalence is. All right. So here's an example. Change in kinetic energy. 1 kilogram ball is fired from a cannon. What's the change in the kinetic energy of that ball as it accelerates from 4 meters per second to 8 meters per second. Now, this supposedly is happening in the cannon itself. It starts from 0, and at some point it's 4 meters per second, but then it keeps accelerating to 8 meters per second. So during that interval from 4 meters to 8 meters per second, we want to know how much kinetic energy did that projectile gain in the process. Right? So here's what it was at the beginning, initial. Here's the final. Right? We have these expressions. Right? So now we can calculate. This is the final, 8 meters per second. This is the initial. Do the calculations. Right? The final is 32 joules of energy. And at the point where it was 4 meters per second, it had 8 joules of energy. So between the time it went from 4 to 8, it gained 24 joules of energy. All right. Now notice that the units here are positive. That means that the system, the cannonball, gained 24 joules of energy in the process. All right. And let's see, let's clear this off. And look at this other example. So in this case, we're going to stop an automobile that's already moving. How much energy is required to stop the automobile? To go from its speed of, let's see, we're given in the picture, we're given the two examples actually. 64 kilometers per hour to 0. Or, let's see, 32 kilometers an hour to 64 kilometers per hour. Okay, so there are two examples here. We have to decide which one is the problem asking for. The kinetic energy of the automobile, of course, is obvious. 1/2 mass times velocity squared. And the work that's required to change any of that kinetic energy is force times distance. Right? So how much force must be applied through a given distance to change that kinetic energy? Force and mass, we say, are going to be constant. Of course, 1/2 is a constant. But the mass of the car didn't change. And we're assuming that the force applied to the brake is going to be constant. If that's the case, then the distance required to stop depends on the velocity, right? If we have force applied through a distance is equal to 1/2 mv squared, and the force applied is a constant, the mass is a constant, then we can say, and this is a constant, then we can combine these three terms into a constant and say d equals m over 2f. F comes over here, m is in the numerator, so this is a constant. And what that means is that the distance required is proportional to the velocity squared. So if we double the velocity, what will that do to the distance? If we increase this by double, then that means 2 squared is 4. So the distance required to stop the vehicle will be 4 times as far as the previous example. At one velocity, it takes a certain distance. If we double the velocity, it takes 4 times the distance. That's why they say when you change your speed from 30 miles an hour to 60 miles an hour, the distance, your following distance to the car ahead, should be increased by, rather than doubling the speed, should be 4 times as great as if you were following at 30 miles an hour, because it's going to take you 4 times the distance to stop if the car ahead of you stops. Okay, that's the point of this illustration, is just to draw your attention to the fact that distance varies as the square of the velocity. Okay, that's kinetic energy. There are other forms of energy that are potential, that is, they are stored and available to do work, but they're not being tapped yet. An object that is moving has energy because of its motion, but some objects have potential energy because of other things. One of those things is its position. And here we are generally referring to position of height. So if we move an object from this height to that height, we have added energy to its potential. Now at this height, it has that much energy added, force applied through a distance, mass times the acceleration of gravity times height will add energy to that object. It's potential now. How do you get that energy back? You just take out the support and let it drop. And it drops through that distance, regains its kinetic energy, or in fact, it has kinetic energy as it falls. It regains that energy, and it now possesses that energy, which it can be used to do work. So that's called positional potential energy. Energy due to its position in a gravitational field. There are other forms of potential energy due to chemistry, right? Energy that's stored in the bonds that hold a compound together, such as nitroglycerin or TNT. The energy stored in those bonds can be released. And when it's released, those two examples give off a lot of energy. Fluid pressure stores energy, right? I don't know if you know about the spy plane, the SR-71. The hydraulic pressure in the lines in that plane that are used to actuate the various control surfaces on the plane, that fluid is under very, very high pressure. And the service technicians that worked on those planes were very careful around the plane not to damage those lines, especially while they're under pressure. If they're under pressure, they knew that a leak in one of those lines, if it struck you in any place, it would cut right through you. There's that much energy stored in that compressed fluid. You can store energy as heat. In other words, if we heat up a rock, then it has the potential to boil water. If it's hot enough, you could drop that hot rock in a pan of water, and the heat would be released into the water, and if there's enough energy, it will boil the water. There's potential energy stored in that hot rock. You can compress a spring, and if you release one side of it, it will release that energy in the form of pushing against something. So there are many ways to store energy as potential. Okay, just a reminder, if work is force times distance, and weight, the force due to gravity, is equal to mass times acceleration of gravity, then all we have to do is substitute the height, movement, and we've done this calculation before. This is just a reminder. We substitute h for d, then the force applied through that distance requires a certain amount of work. And you store potential energy by moving an object up against that gravitational field. So weight times height is your potential energy. Right? So the potential energy is this mgh. So here's an example. How much work has to be done to lift a 1 kilogram book a height of 1 meter? Okay, it's simple. You know the kilogram is the mass here. You know the height, the distance moved in that gravitational field is 1 meter. And we know what g is, 9.8 meters per second squared. So all you have to do is multiply them together. And work is the units of joules. So kilogram meters squared per second squared is a joule. And the work done to move that book is 9.8 joules. So now the book, we have stored an additional 9.8 joules in that book by virtue of its position. And if we release the book and let it drop that same distance, it will acquire 9.8 joules of kinetic energy just before it hits the ground. Right? When it hits the ground, then the kinetic energy is converted into something else because it's not moving anymore. And that's a law that we're going to express here in a few minutes called the conservation of energy. We cannot destroy energy, we cannot create energy, we can only change its form. So the amount of energy that's released if the book is dropped through that same distance is 9.8 joules. Now, this illustration says that the potential energy stored in this object is by virtue of its change in height, vertical height against that pull of gravity. It doesn't matter how it gets there. It can go from an angle of any type to that same height, and the amount of energy stored is exactly the same. That's known as a state function. And a state function simply means that we only care about the state before and after. What was it before? It was down here on the floor. What was it after? It was up here at this height. The state before, the state after. What happened in between doesn't matter. If we describe a function that does depend on what happens in between, then we call that a path function, because the pathway that it took to get there does matter. But in this case, the stored potential energy does not matter the pathway. It's a state function. And of course, we have to disregard the losses of energy due to friction. See, this is a theoretical problem. So we ignore friction for the purpose of the solution to the problem. Okay, so if work done is a change in potential energy, we get this formula. Work is equal to mg delta h, a change in height. So suppose the object is already at this height. Well, it has some stored potential energy between there and the ground, but we want to find out how much more potential energy does it gain by virtue of moving it to a new height. If the previous example, the height is h, then the change in h is what it was it before, what is it after, right? Always the final minus the initial. So we just choose the reference point. You may consider it arbitrary, or we might have good reason to pick a reference point. But it must be consistent. In other words, a reference point from here to here, this is 0, and this moves to a new point. And then if we say we want to go from here to here, our new reference point now is this level up to that point. Our original reference point was here. So we're going from 50 to 100. We've moved 50 meters, right? Our new reference point is picked to 0 for here. If we want to know the total change, then we go from here to here and here to here. And we can either do the calculation from this 0 to that final, or we can do it in steps. We can say the gain in potential energy from here to here is a certain amount, and the gain from here to here is a certain amount, and the summation of those two is equal to the total move from 0 to 100. That's because we're dealing with a state function. It doesn't matter how we got there. The summation of these movements is equal to the total. All right, so, I've already described some of these types of potential energy. Compressed or stretched spring will store energy. The bowstring on a crossbow or a standard bow will store energy until you release the arrow. Chemical energy, I've described that before. We store energy in the chemical bonds that hold the compound together. Fluid pressure, I mentioned the hydraulic pressure in the lines of that SR-71 airplane as a very, very high pressure, so there's lots of energy stored there. We can store energy in terms of heat, a change in temperature. Electrical charge can store energy too. So if we have an electrical device called a capacitor, so we have two plates here. This one is positively charged, this one's negatively charged. So we build up negative ions on this side and an absence of charge on this side. And there's a potential energy built up between those two plates by virtue of the fact that these two charges are attracting one another. So we have stored energy in that capacitor. There is stored energy in sunlight, radiant energy, or in some light bulb as it generates that light. So the light coming to us from the sun has stored energy in it, and we have to extract that energy in some form or fashion. We could use it to, actually plants use that radiant energy and convert it into chemical energy by some biochemical means in their leaves. Or we can convert radiant energy to electricity through solar cells. There is stored energy in the nucleus of the atom, and we can tap that energy by splitting the atom. If we break an atom apart, or it spontaneously breaks apart, it will give up some of that energy in the form of, usually in the form of heat, or in fast-moving subatomic particles. Now here's that law that I expressed earlier, the conservation of energy. We cannot create energy, we cannot destroy energy. The total amount of energy in the universe is constant. It does not change. And that's actually the first law of thermodynamics, which says that the total change of energy in the universe is 0. There's a certain amount of energy in the universe, and it does not change. We can move the energy around on the local level, but we cannot create it. We cannot destroy it. And that energy is always conserved. It's got to go somewhere. It's like a budget. If you spend it here, it ends up over there. So the total energy at this time At some later time, it's the same total energy. We can narrow that discussion to mechanical energy. Mechanical energy can be conserved also. And when we say mechanical energy is conserved, we usually mean the interchange of energy between kinetic and potential energy. In other words, the potential energy that an object has, say, with reference to its height, if it drops through that height, then that potential energy of position is converted into kinetic energy of motion. Right? So we have its kinetic energy at the start plus its potential energy is equal to its kinetic energy at the end plus its potential energy at the end. Right? So its final conditions, the total energy here is equal to the total energy there. And the potential energy due to height is mass times the acceleration of gravity times its height, and its kinetic energy is 1/2 mv squared. So at the beginning it has these two, and at the end it has those two, but they both together must add up to the same value. Now, if it's at rest at this height, then this value is going to be 0, and it's all stored here. And if you drop it through that height to this certain level, then all of that potential energy, this goes to 0, and now it's all over here. But in between, there is a mix of some potential energy due to height and kinetic energy due to its motion. So here's an example. We're dropping a rock from 10 meters to 0 meters, and at some point through here, this rock reaches 3 meters from the ground. Okay, 3 from 10 is 7 meters. It's traveled 7 meters, and that amount of stored energy now is converted into kinetic energy. Okay, and of course we have to neglect wind resistance and other mitigating factors in order to rationalize this problem. So its total energy is going to be the same no matter where it is in its height. The kinetic energy plus its remaining potential energy will always be this total value. Okay. When the stone hits the ground, right before it hits the ground, all of its potential energy is converted into kinetic energy. And one good illustration of that interchange of potential and kinetic energy is a roller coaster. Right? If you have a roller coaster, what's the first thing that happens when you get on the roller coaster and it starts to move? You go like this, and then you go up to there. You go through this height, and you store energy in that roller coaster up to that height. Then it goes down, and it goes down, and it goes down, and around, and around, and around, and around. It comes back to this position right here. Okay, all of that energy that was stored here now is kinetic energy at the end. Of course, minus some friction. Okay, but all the energy that was stored up here is used to move the coaster through these different changes in direction and loops and what have you. Okay, so for this example, we have a rock that is at 10 meters, and we're saying now that the rock weighs 1/10 of a kilogram. Okay, so now that we can do the calculation, we know that its potential energy was 9.8 joules when it was at this height right up here. That's how much energy is stored. And no matter what happens between 10 meters and the ground, that amount of energy is the total. Right? So when it moves to 7 meters, it now has only 6.9 joules of potential energy remaining. What happened to the other 2.9 joules? That 2.9 joules was converted into kinetic energy of motion. Okay? And now at 3 meters height, it only has 2.9 joules left of potential energy. The 6.9 joules between the top and this position now is converted into kinetic energy. And when it stops at the bottom, there's no more potential energy. It's all kinetic energy. Okay? And this little table sort of illustrates at the different heights, the total energy is always 9.8, 9.8, 9.8. Okay? That's the total. At the top, all of it is potential energy and none kinetic energy. At the bottom, there's no potential energy left and it's all kinetic energy. But at every stage in here, the summation of the potential plus the kinetic energy is equal to the total. Okay. Now, if you look back to our second chapter where we were studying kinematics, we had formulas that were telling us how fast things were moving, for instance. Now we know why they're doing that, because there's an interchange of energy. Okay, potential energy again is mass times the acceleration of gravity times change in height. And the kinetic energy at any one place is 1/2 mv squared. We can use these two equivalences to compute the speed or the magnitude of the velocity at any one point. Right? So if we set these equal to one another, which will always be the case, no, that'll be the case when it hits the ground. How much potential energy did it have? Now at the ground level, this is the velocity that is moving at the end of its journey. Okay, so 1/2 v squared. If we move the mass over here, then it cancels, right? This is just simple algebra. If we have the kinetic energy on this side and the potential energy on this side, then these two masses cancel. Correct? That gives us 1/2 v squared equals gravity times change in height. So now if we solve for velocity squared, we have g delta h divided by 2. Excuse me. My mistake. 2. This is in the denominator. Now it's in the numerator. 2g delta h. And then if we solve for a velocity, we have square root of 2g delta h. This is another illustration of Galileo's principle. When he dropped two objects of different masses, they hit the ground at the same time, which means they had the same velocity also. So all you have to know is the height and the acceleration of gravity to know what its final velocity is. It doesn't matter what the mass is. Okay? So this formula will tell you what the final velocity is based on the height in this gravitational field. Now this is good for Earth because we know that's 9.8 meters per second squared. But on some other heavenly body like the moon, if we know what g is on the moon, we can calculate its velocity based on the height, the change in height. Right? So this formula is not restricted to the Earth. It's only restricted to the Earth if we assume that g is 9.8 meters per second squared. Okay. Now we've defined what work is. We've defined kinetic energy, potential energy, positional potential energy. Now we're going to go one step further. We're going to say, how fast does this change occur? In other words, we expend energy to do work. Well, we can expend energy at a very slow rate and do work slowly, or we can expend energy at a high rate and do work fast. You can do the same amount of work in less time. The expression for that is called power. And power, in its simplest definition is the time rate of doing work. So power would be whatever work is divided by the amount of time it takes to do that work. So work divided by t, or force times distance divided by t, is the definition of power. So you notice that if you expend a certain amount of energy, but you do it in less time, then the power rating is higher. If you take more time, then the power rating is lower. The standard unit of power in the international system is the watt. It's joules for work divided by the standard second time. Okay, this is a derived unit. It's derived unit from derived units. The watt is 1 joule per second. And we can equate various forms of energy and power usage simply by knowing the rating. So a 100-watt light bulb means that it consumes 100 joules per second of electrical power, or 100 watts. It's important now that we've introduced this unit of measure for watts that we don't get it mixed up with the variable for work, the W variable. So that's why this one is italic, if you can see it leaning, and this one is non-italic for watt. And very often you can tell the difference because of the context. Okay, so in this example, this man is lifting a weight through a distance of 1 meter, and he is applying 1 Newton of force to do it. So a Newton meter is a joule, and 1 joule is applied over a time period of 1 second. So he is expending, his power rating is 1 watt in performing this task. Okay, this just illustrates the conversion of units, right, which I've done before, and it's important to recognize that these derived units are related to one another. Force is a Newton, right, and a Newton is equivalent to a kilogram meter per second squared, based upon Newton's second law. Meter per second squared times kilogram. That is a Newton. Okay? Work is a Newton meter. Force times distance, which is a Newton meter. A joule is also a Newton meter. And a watt is a joule per second. So it's a Newton meter per second. Right? Or it could be a kilogram meter squared per second squared per second. So it'd be a second cubed. So we can carry this on to a ridiculous extent, but it's important to recognize that these units are interchangeable. Not interchangeable, I should say. They are relatable by their derivations. Their fundamental units hold them together and relate them to one another. Now, just for illustration purposes, because in the United States, we still adhere to the British system for many of our units of measure. The work is a foot-pound. Power is a foot-pound per second. Okay, but we also have other units, derived units from that. The horsepower was derived from foot-pound per second, and 1 horsepower is 550 foot-pounds per second, or equal to 746 watts. So now we're converting from the British system to the international system, or the metric system. So that gives you a conversion factor. Remember, this is an equivalent. That is equivalent to that. You have a conversion factor available to you. Now, the story of the invention of the unit horsepower dates back to the invention of the steam engine. Everybody understood before the steam engine came online as a means of doing work, all we had was muscle power, either human muscle power or draft animals. Everybody understood how much work a horse could do in a day. So the inventors of the steam engine, I can't remember which one it was at the moment, decided we need to, in order to sell our steam engine as a substitute, we need to be able to relate it to what people already understood. They understood horsepower. So they set up experiments, and they said, how much energy, how much work in a period of time can this horse do? And they equated that horsepower to the new value of watt. And then they could sell their steam engines in terms of horsepower. What is its equivalent horsepower? Now we have engines in our cars that will that are rated at 200 or better horsepower. Some of the smaller engines are like 150, 140, 130. But some of them are even higher than that, 300, 350. And that's where that value came from. The greater the power of the engine, the faster it can do work. So a 2 horsepower engine can do work twice as fast as a 1 horsepower engine. All right. Now, most engines, and you look at any automobile magazine, Car and Driver, for instance, when they discuss the power for a car that they're rating, they will give you the rated horsepower, and they'll give you the torque that can be produced by the engine. Remember, we defined torque as a force applied through a lever arm. That is basically a force. That is what's moving, what is pushing through the drive shaft of the engine. That, in effect, is what moves the car, is torque. That's what moves it. That's what makes it go. The horsepower rating, it says, all right, once you've got it going, how fast can you get there? That's the power rating. So it's important to say that torque is what moves the vehicle from A to B. In other words, if you have a vehicle that weighs so much and the engine is so small, the torque is not sufficient to move it. So if I tried to put my lawnmower engine in a semi-trailer truck that is fully loaded, then it probably won't move. There's not enough torque. So the horsepower is irrelevant. It's not going anywhere with that engine. But if I have a large enough engine under the hood and the torque is sufficient, the force will move the truck, then the horsepower, the power of the engine becomes relevant and says, all right, now that it's moving, how fast can we get there? Okay, calculating power. We've defined what it is, so now we need to apply that knowledge. If there's a constant force of 150 newtons pushing against this motorcycle for 10 meters along a flat road at 20 seconds, and it takes him 20 seconds to go 10 meters with that force, what is the power that's required to do it in that amount of time? Right? There's your force, there's your distance, so that's your work, and this is the amount of time it takes to do it. So it's a very simple calculation. You just have force times distance divided by time, and you check your units. Force is in newtons, yes. Distance is in meters, that's good. That's the standard unit. Time is in seconds, we're good to go. Do the calculation, and the value of 75 watts is the amount of power required to move that motorcycle 10 meters in 20 seconds. Now, remember that this is derived from a formula. That power is equal to force times distance divided by time. Force times distance divided by time. So if we want to get there, in 10 seconds instead of 20 seconds, how much power do we need? We need twice as much power. We need 150 watts to apply 150 newtons through 10 meters and get there in 10 seconds instead of 20. So you have to double the power. Well, if you only have that same amount of power and you want to apply less force, then it's going to take you twice as long. So 75 watts for 10 meters, 75 newtons, excuse me, 75 newtons for 10 meters will take you 40 seconds to get there. So that's a mathematical formula, and we know that if we can fill in all but one of those values, we can solve for the unknown value. Okay, so in this case, we're saying that a student expends 7.5 watts of power in lifting a textbook a half a meter in 1 second. How much work is done, and how much does the book weigh in newtons? Right? So we know the power that's required, we know the distance that it's moved, and we know the time. Right? So we need to find work first, and then we want to find the weight. So if we know work is equal to power times time, because if power equals work divided by time, then we can solve for work, because that's what we want to know. We want to know how much work is done. So it's power times time. So we say power is 7.5 watts times 1 second. The work done is 7.5 joules. Okay. Now, if we want to know how much weight, we can apply another formula. Work is force applied through a distance. Right? So work is force applied through a distance. We want to know the force or the weight of the object. So force is equal to work divided by distance. So we calculated the work at 7.5 joules. Now we know the distance as a half a meter. So we divide a half a meter into 7.5 joules and we get 15 newtons. So now we know that the book weighs 15 newtons. Okay? All right. So let me see how I'm doing on time here. All right, we're about finished with the theoretical discussions, and we're going to look at some practical implications relative to energy. But first, let's talk about electrical energy. Power, of course, is energy produced or consumed over the amount of time taken, right? So that's energy per unit time, which is equivalent to work, because energy is the potential to do work. So we can look at the potential for the electrical energy based upon how much energy there is expended in a certain amount of time, right? So now we have energy equals power times time. And if we substitute values, here for power and time, we have watts. Right, we have watts times seconds. And if joules per second is watts, then watts times second is equal to joules. So that's energy, that's work. So we've reconciled the use of power times time as an energy value. We could say watt seconds is a value of energy because we know that the units reconcile. Okay, but for energy consumption nowadays, we need bigger units. So instead of watts, we use kilowatts, 1,000 watts. And how many hours do we use that? That gives us the amount of energy. So kilowatt hour is actually a unit of energy, a derived unit of energy, potential for doing work. So that's why the meter on the side of your house reads off in kilowatt hours. That is a measure of energy, not power, energy. So that's what you pay for when your electric bill comes due. You're paying for kilowatt hours. So, and that's convenient because the units of measure for calculating work and the necessary input of energy are in these larger value terms. In other words, you may run a 1 horsepower motor for 10 hours, right? So you've got the hours value here. You just need to know how many kilowatts is 1 horsepower, right? So we know that the relationship between watts and kilowatts is 1,000 to 1. So here we change to watts, but we also know that 1 horsepower is 746 watts. So once we do the conversions, we find that 1 horsepower is 0.75 kilowatts. Okay, and a kilowatt for 10 hours is 7.5 kilowatt hours. Okay, so that's how much energy is required to run that 1 horsepower motor for 10 hours. Okay, this just re-emphasizes the fact that we have to conserve energy. That's the law. We cannot create it, we cannot destroy it, we can only convert it. And we can convert it amongst these various forms, mechanical, electrical, chemical, whatever else. We can convert energy. Of course, when we do that conversion, and this isn't part of the main discussion, but it's important to recognize that whenever you convert energy, you always lose a little bit of something in the conversion, right? Theoretically speaking, we convert all of it from one place to the other. But as a practical matter, you always lose a little bit in the transition. And that's a discussion for, actually for a more advanced class. Okay, what forms of energy do we have available? Well, thermal, heat energy, and that can be related to the kinetic and the potential energies on the molecular level. So the kinetic energy on the molecular levels, how fast are those molecules moving? They all have kinetic energy. But they also have potential energy in terms of transferring that heat to some other form. We've talked about positional energy, which is gravitational potential energy. Electrical energy, right? Based on say a charge in a battery. A battery has stored potential energy. Or actually, in a hydroelectric dam, you have stored potential energy due to the height of the water above some level, and as the water drops through your turbines, you convert that stored potential energy into electricity. Chemical energy is due to bonds inside the molecule. Radiant energy in the form of photons coming from the sun. Nuclear energy is actually energy stored in the nucleus of the atom. So nowadays, we most efficiently gain that energy by fission. That is, we split atoms apart. But there's work being done to fuse nuclei together. When you do that, you also gain some energy back. The stars do it all the time. That's how they make their energy, by fusion. We've only managed to do it on a very small scale in the laboratory. Okay, what types of fuels are there? Where does our energy come from? Well, most of the energy that we use these days is fossil fuels. Fossil means stored in the ground, right? It's been fossilized. These fuels are stored in the ground and we extract them. They could be oil, natural gas, coal, or fossil fuels. And the theory is that they were once living organisms that were buried in the ground. They had stored solar and chemical energy in their tissues, and then they had died and been buried. And that energy is fossilized. It's stored in some form in the ground, and we extract it and then use it to do work. Oil is believed to be derived from marine organisms. In other words, swampy waters. And they were eventually buried. We had managed, prior to the presidential elections in 2020, we had managed to reduce our imports of oil to zero because we were producing that energy ourselves domestically. Since President Biden took office, we are now a net importer of that energy due to his policies, which is another discussion. Gas also is believed to be derived from marine organisms. And that also means that we were a net exporter of gas until President Biden took office and initiated his war on fossil fuels. Coal, of course, is still a huge supplier of energy in this country. And it's believed that coal was originally formed by land plants that died and were buried, and now must be extracted from the ground. There are basically two ways to do it. You can tunnel into the ground and dig it out, or you can just take the top layer of soil away and scoop it out. There's another form that's a curiosity at the moment. It's called methane hydrate. It's a combination of water and methane in frozen form, and it's found at the bottom of the oceans where the temperatures are very, very low. And natural gas can be extracted from them. There's some research being done on it, but it's not a practical supplier of energy yet. This is just an example. This is what it takes to get oil out of the ground. Once you drill the well, and then you set up these pumps, and they pump at various rates depending on how easy it is to get the oil out of the ground, and they lift it to the surface, and then we have to distribute it somewhere. This is a what's often called a Christmas tree. This is the wellhead for natural gas. Because it is a gas, as long as it is being freed from the strata underneath the ground, then it flows out freely under pressure. Here's a coal seam. Right? So, and this is obviously a road cut that cut through a coal seam. This is not a very, well, it looks like it's maybe 3 to 4 feet thick. That's often called low coal. I don't even know if it's economical to even go after coal that thin, but that coal bed is exposed there in a road cut. This is the consumption of different types of fossil fuels. We're still highly dependent upon oil, although natural gas and coal are substantial amounts. 50% in combination. Nuclear was gaining ground for many years until several accidents set it back. And the building of a nuclear power plant is administratively difficult. Governments make it that way because it's politically expedient to suppress nuclear energy. The public doesn't understand it. We have safer technologies now, and we could be using more nuclear energy. And for those who believe in man-caused global climate change due to production of carbon dioxide from fossil fuels, should be all in favor of nuclear energy. So if you want to find out if a person is really serious about carbon dioxide emissions, ask them where they stand on nuclear energy. If they do not support nuclear energy, then their support for reduction of CO2 emissions from burning fossil fuels is a lie. If they do not support nuclear energy, then they're lying to themselves and to you about the effect of carbon dioxide on the environment, because nuclear energy does not produce carbon dioxide. All right, for the generation of power, electrical power, coal is still king. Natural gas is useful, and it's cleaner burning than coal. But the generation of electric power is also substantially due to nuclear. Not so much in this country, but worldwide, it's still produces a big chunk of electrical energy. Hydroelectric energy has reached its limit. The economically developable sites for hydroelectric power have all been used up. You need a place where you can store water at a sufficient height to drive your generators. And those places on rivers all the good sites are taken. Oil doesn't produce much electrical energy. It's used in other forms. Now, where is that energy consumed? Well, a very large chunk of it is industry. Transportation takes a big share, and commercial and residential uses also take a big share. They're about equal, a third of each. We define some terms. Alternate energy sources. What they mean by alternate energy sources are those energy sources that are not fossil fuels or nuclear. So anything that's not fossil or nuclear is considered alternate. And many of those overlap with what we call renewable energy sources, those that cannot be exhausted, such as solar energy or biomass or various other types, geothermal. We'll talk about those as we go along. Now, like I've said before, the issue of global climate change is a controversial subject, and the controversy lies around who's causing it. Is global climate change caused by natural processes, which I believe it is, by and large, or is man responsible, which I think is a ruse. There is, regardless of what the popular literature says, newspapers, talking heads on television, there's no proof, there's not even consensus from the scientific community that man-caused global climate change is significant. They're basing their predictions upon models of climate change. Now, these are mathematical programs that are built into computers, and the factors are fed into it. And if you make measurements in the climate and put them into this model, it spits out a number. It says, okay, over the next 100 years, the climate is going to warm by 5 degrees Celsius. Well, the fact of the matter is, we've been using these models for many decades. So we have built up a pattern from earlier times to now, and we can put those values into the models and say, can any of them predict where we are now? And they all fail, every one of them without exception. They never predict the right answer. So that just tells me that the models should be junked. They're not worth tweaking anymore. And the reason is that they're chasing the wrong culprit. They're saying that man's activity is causing global warming, and they will tweak their models to give you the answer they want, while the models themselves are really just mathematical constructions. They really ought to be looking at the real influencers on climate, right? Those major factors are solar radiation, number one. That's something we have no control over. Cloud cover. More clouds reflect more energy back into space. Clouds also trap energy that's already here. And then there's water vapor. Based upon the intrinsic value of water vapor as a trapping medium for heat coming from the earth, water vapor in its intrinsic value and in its magnitude are far more, the water vapor is much more effective as a global warming molecule than carbon dioxide, much, much more. The theory is that when solar radiation strikes the earth, right, it heats the earth up, and the heat is re-radiated at infrared levels. So it comes in as visible light, and it's re-radiated as infrared. So infrared can be reflected back to the earth by molecules in the atmosphere. CO2 does, water vapor does, and there are several others. Methane, in fact, is more effective at trapping infrared radiation than is carbon dioxide. But there's so little carbon dioxide in the atmosphere, around 420 parts per million, which is very low, whereas water vapor is in percentage amounts, high percentage amounts. So water vapor is much more effective at trapping. And how do we control water vapor? Well, 2/3 of the Earth's surface is covered in water. How are you going to change that? So the argument that man is causing global climate change is ridiculous on its face. If we go to the geology, the geological record, there is a correlation. Now, if anybody in here has had statistics, you know that correlation just says that things happen together. They're correlated. Right? It doesn't say one causes the other. There's a correlation between carbon dioxide levels and average global temperatures. But there's no causation. In fact, there's evidence that the global warming happens first in geological time, followed by an increase in carbon dioxide. Okay, there are many of us, I'm included, that believe that this Kyoto and Paris Accords for the reduction of carbon dioxide emissions in the world are merely a planned redistribution of wealth on the global scale. In other words, developing countries don't have to abide by the Paris Accords. They can pump as much carbon dioxide into the air as they want. As long as they're identified as developing countries, they're free to pollute all they want. Whereas the developed countries must control their carbon dioxide outputs. What that does is that suppresses the economies of the advanced countries and accelerates the development of undeveloped countries, which basically redistributes the wealth of the world toward those undeveloped countries. Now, countries like China that claim to be developing, which they're not, they will go ahead and build 5 factories a week, 5 power plants, coal-fired power plants a week, and just pollute till the end of time. All they have to do is claim that they're a developing nation. All right, so that's why the Kyoto and the Paris Accords are bunk, in my humble opinion. All right, other forms of energy. I mentioned hydropower, right? This uses the gravitational potential energy of water flowing downhill, which is converted by generators into electrical energy, right? The best sites for these dams, these hydroelectric dams, are already taken. You can't build anymore with our current technology. There are questions of environmental and ecological damage, right? Whenever you throw up a dam, you flood a region of land that was once arable. Many times it's farmland or land that was once used for habitation. And as water moves downhill through its channel, its rivers and creeks and streams, it carries a load of silt, that is, solid particles of soil. And as long as it's moving, they will stay suspended. But when that water reaches the reservoir site for behind a dam, it stops moving. It moves much more slowly. So the sediment load drops out and coats the bottom of the reservoir. Eventually, depending on the sediment load in the water coming down, the reservoir will be silted in. In other words, the bottom will rise, which means that you can't store as much water in it, and you can't derive as much energy from it. So you have 2 choices. Either you abandon the dam at some point, or you go in and dredge it out. This is a type of dam. Notice there's a narrow gorge here, and the dam blocks the way, and the reservoir behind it stores the energy of the water. Now, these dams, many of them serve a dual purpose. They're also for flood control. In other words, seasonal floods cause devastation downstream for many of these rivers. So if you put a dam in the way and let the water come out slowly, controlled, then you can manage the land downstream to the advantage of people living there. This is another type of dam. Wind power is reported to be a useful renewable source of energy. It's not particularly aesthetic. I mean, especially if you have a lot of wind turbines sitting on the top of a hill, they're kind of an eyesore. Plus, they make sound, and they cause light flicker in the moonlight, so they can be disturbing to some people. They have to be placed where the wind is fairly constant. And on the surface of the earth, there are very few places where that's true. Now, if you can get your wind turbine at 1,000 feet or higher, then the wind is constant. And there's some work being done for that, also testing there. Wind power has been used for thousands of years to do work. Grinding grain, we all think of the Netherlands with their windmills. They use them to grind grain and to pump water, because the Netherlands is basically a floodplain. So they pump water, they build dikes, and they pump water out using this wind power. Some of the detrimental effects, you have to have lots of these bladed turbines set apart by about, if you've got one setting here, then you've got to be 10 blade diameters behind it before you can put another one, because the interference of the blade with the movement of air makes the one behind it less efficient. So if you put it 10 blade lengths behind, then things have settled down and it can extract its maximum amount of energy from the wind again. These spinning blades cannot be detected by birds easily. And even bats get confused by them with their sonar. And lots of wildlife is killed by these spinning turbines. I mentioned the light flicker. General aviation, they have to be well lit and identified so that small planes flying at low altitude won't run into one of them. There's also the economic issue. These wind turbines are high tech. They use some exotic materials, particularly to make the magnets and the electronics controlling them. And that requires lots of polluting manufacturing techniques. And there's high cost involved, there's high maintenance involved, and then at some point, these turbines don't function efficiently anymore and have to be retired. So you've either got to recycle the materials, or you've got to find a way to junk them. So you have that environmental hazard also at the end of life. So there you have a whole hillside full of the things in California. Here we have, and these are 10 blade lengths apart, like I said before. It's 12:30 appointment, isn't it?
Yeah, it's 12 o'clock. Doesn't Paul Henry have one today too?
Yeah, later after we get back.
Oh, okay. What time?
5:45 for Paul Henry.
Oh, late appointment.
Now we have solar power. That's a possibility. Solar power is a reliable source of energy, as long as you don't have a lot of cloud cover. Then you can extract energy from the sun. There are basically two ways of doing that. There's the photovoltaic cell, which converts light directly into electricity. And then there's the concentrating solar thermal plant, which basically takes the energy and reflects it with lots of mirrors into a concentrated center and boils water or some other fluid, heats up the fluid so that it can drive a generator. And depending on where you are and what your resources are, one of these works better than the other. Of course, with concentrating solar thermal plant, you usually need a water source, whereas photovoltaics can be done in the desert. There are various problems. The main problem with solar power is low energy density. In other words, for a square meter, there's not very much power reaching the surface of the earth. Very low energy density compared to fossil fuels. There's the efficiency of the photovoltaic cell itself, which has been improving over the years. It used to be less than 5% of the energy striking the voltaic cell was converted into electricity. Now we've got some experimental versions that convert up to 50%. But that efficiency decreases over time. So eventually the photovoltaic cell, starting off at high efficiency, ended up at low efficiency and must be retired for economic reasons. And there's the issue of land use. You know, what other possible uses for that land are there? Are they more economical than the power use? Is it farmland? You don't want to take up farmland for solar cells. So the photovoltaics and the concentrating solar thermal plants are usually located in areas where it's uneconomical to farm. The photovoltaic cell itself is a very high cost of production. And at least for the near term, it must be subsidized. People cannot afford to buy photovoltaics for their homes, and big power companies cannot afford to build large photovoltaic solar power plants unless they're subsidized by the government. So they cannot stand on their own, economically speaking. And since their efficiency decreases with age, then once you've amortized the cost of this production of the plant, eventually you've got to retire it anyway. And the photovoltaics in particular have very high end-of-life hazardous waste costs because they're produced with heavy metals, and heavy metals are a known pollutant. So you've got to do something with the waste. Okay, geothermal energy is very site specific. There are only very few places on the surface of the earth where you can access geothermal energy. Right? Usually you need tectonically active areas, like certain parts of California, Yellowstone is geothermally active. Iceland is active, and they use geothermal there. But you need a large temperature variation at shallow depth to be economical. This one's located in Hawaii. Of course, Hawaii is a hot spot, so they have access to geothermal energy. Yellowstone. The problem with Yellowstone may be near term, it may be long term, but Yellowstone is the site of a supervolcano, which last erupted about 640,000 years ago. And it's on a 640,000 year cycle. So we're expecting one anytime now. So build your plants there and just hope the thing doesn't erupt. There's tidal energy, right? As the moon circles the earth and the earth rotates with the influence of gravity from the sun. We'll talk about this in a later chapter. You have tides built in. Water is moving in the oceans and the inlets. and that can be accessed. But in order to make it work, you've got to have turbines that will work in both directions, because the tide moves in, the tide moves out. And there's some places that have been generating tidal electrical power for many decades. Okay, biofuels. A biofuel is anything that is once immediately living. Corn, sugarcane are common plants. There are some grasses that are being investigated. You can either burn them directly and produce heat, or you can convert them to other types of fuels like ethanol. And nowadays we combine that ethanol with gasoline and burn it in our gas tanks in our automobiles. Unfortunately, the cost of production of ethanol very often exceeds the amount of energy required to produce ethanol is more than the energy gained by burning it. So it's a net economic loss. That means it must be subsidized by the government. If it's not subsidized, then economically speaking, it would go out of fashion very quickly. Okay. Biomass is renewable, and it takes many forms. Some agricultural crops, right, use corn for gasohol, which is kind of a stupid way to use corn, because it's more efficient to feed it to people and animals than it is to convert it into ethanol. Wood products, animal waste, even municipal wastes like sewage, aquatic plants. Any of these biomasses can be used to extract energy. Single source biomass is currently unworkable. It only exists with government subsidy. But supplementing energy streams with some biomass can be made economical, but it's only on a localized and limited basis at this point. So here are the formulas that we've covered today, listed for you. You need to know what they mean, know how to use them, and work lots of problems with them. And then you'll get comfortable with using them if you work the problems. If you don't work the problems, then come test time, you will be completely lost. So I say work as many problems as you can.